All right, welcome everybody. I think now we start this webinar. It's 2 p.m., so it's right on time to do this webinar regarding cavitation. My name is Stéphane Blanchet. I will be your host today with Lorraine here, our product specialist. And we will discuss about cavitation. So obviously it will be quite focused on our own products, our own product valves, but we will discuss also a lot about what is cavitation, what is it exactly, so a lot of technical stuff, and also how to manage it, how to do the sizing and so on. So yes, Loan, you can go to the next slide. That is the agenda for today. Yes, so a brief presentation about the company. I think most of you know the company, but for those who do not know, it will be quite a quick presentation. And then when we do an introduction about the platform, our product platform, where you can find our products, everything related to our products, in fact, technical things, sizing tool, pricing, and so on. We will discuss also about cavitation because that's the main topic, obviously. That will be the main focus today. And we have some question and answer at the end of the webinar. So you have the chat function on the top of your screen normally, so you can always click on it, ask a question, and then we will review it at the end of the meeting. So it should end up at 2:30. But briefly about ramen valves, very quick because there is a lot to discuss. So the company has been created in the 1940s, so you can see that it's quite old company. We are located in Stockholm, where we have our main office, and we have also manufacturing site in Sweden, where we do the production. Quite small company, relatively small company with 12 employees, and we sell worldwide. So obviously in northern countries, because that's where we are located, but obviously also all over the world with our partners. So Ramen is a producer of valves. So we produce our own ball sector valves, so that's control valves, but also check valves, vacuum breakers as well that we produce ourselves. And we also distribute valves products from our partners. So that's, for example, Erose safety valves, Erose process valves, but also Cashco pressure regulators, badgeometer control valves, and so on. So that's who we are. Yes, Lorraine, you can move on.
Okay.
Yeah,
Right.
so that's on you now. You can continue.
Right. So I'm going to. My name is Lorraine. Good afternoon, everybody. I will first and foremost just go to the website. So at ramenvalves.com, you will find a lot of information and a lot of stuff information about valves and valve solutions. And now we're running information on hydrogen. You're welcome to go and read up on that. If you want to go to the product platform, you can select any of the products, and it will take you immediately to the product platform. Okay. Sorry, on top. And then on the product platform, you can choose valves, process valves, regulators, safety valves, tank safety equipment, and spare parts. I just quickly want to show you how it works. So we go to control valves, and you can then select whatever control valve you want. In this case, just quickly select a Ramen KC valve, and it will take us to a configuration. So in the configuration tab, we can select a modulating valve, size DN50, soft seated design, single acting, 420 milliamp, and immediately it will give us all the technical specifications here. You can get some more information there, and then at the bottom you will find data sheets, instruction manuals, certificates, brochures, 3D step files. You can also compare this to another valve if you want to. On top you will see the price, which is related to whatever discount you are registered with, and then the article number you will find there. If you need any information, you can just contact us, and we will help you. On the right-hand side at the bottom, it's easy to just write us a message. Okay, let's go to the sizing. So from here, you can go to the control valve sizing. I've already opened it, so I'm just going to jump in and go to the sizing tool. So the sizing tool is a highly specialized sizing tool from Conval. It is a very professional sizing tool, and we suggest that you make use of it as much as possible. First of all, you would like to change your units. You can select imperial or USA units, or you can select metric units. In this case, we selected metric units. For cavitation, we're going to make it easy, and we're going to do just plain water. We select water. You can just type in water by name, or you can go and search for it in the 3 dots on the side, and then you can search for the fluid that you want to size for. Design data we're going to use as 50 degrees Celsius, and maximum design pressure 16 bar. So let's quickly go through the process data. We're going to have 3 points, a maximum mean flow and a minimum flow. And we have 25 degrees on the inlet. We have 6.5 bar for the maximum flow, 6.3 for mean flow, and 6 for minimum flow. We have bar gauge. This is pressure control, so we will have all on 4 bar for the outlet pressure. Our flow rate is volumetric flow rate, and it's 150 at maximum flow, 100 meter cubes at mean flow, and 75 meter cubes at minimum flow. So I'm not going to go into and select the product right away, but at this stage, as you will see, we have information that says we have incipient cavitation. So let's go to the details, and we go to the next slide, and we will discuss from here. So let's first ask ourselves a question: what does cavitation look like? Cavitation is a rough mechanical erosion, and it looks like pitting, as per the picture on the left. Where it differs from flashing, is a smoother knife through butter effect on the plug and the seat. Many of you have probably seen this and wonder what happened to your valve. Now, the definition of cavitation is the rapid formation and collapse of vapor bubbles within the liquid. So to understand that, we first have to just go to vapor pressure, and to do that, we're going to look at the phase diagram of, let's do this now for water. So the phase diagram shows us where the solid ice goes to water, water goes to a vapor, and either or backwards. So in this phase diagram, we also is included is the vapor pressure curve. And above and below that curve is the vapor and the liquid phase of the fluid. So the effect of constant pressure is at 1 bar, water will melt at 0 degrees Celsius and will evaporate at 100 degrees Celsius. The effect of constant temperature, where the pressure changes, water can boil below 100 degrees Celsius, and water turns to a vapor form. So how does cavitation occur? So when flow passes through the valve restriction, the plug in the seat, from high pressure, P1, to a lower pressure, P2, the pressure decreases and to a point of minimum pressure. As the pressure decreases from going from P1 to P2 flow rate, the velocity increases. The point at maximum velocity and minimum pressure is your vena contractor. You also notice that your vena contractor is downstream of your orifice, not exactly at the orifice. So when the pressure drops below the vapor pressure, so we have 3 graphs on the side. So here our inlet pressure goes down to the vapor, to the vena contractor, and to the lower P2 pressure. It does not cross the vapor pressure. At this point, the second graph is our vapor pressure, and vena contractor is the same point. So that is almost where the cavitation will start. The third graph, you will see that P1 crosses the vapor pressure, a bubble forms, and it recovers downstream, and the bubble being imploded to P2. And that is when cavitation starts. So the first step of cavitation is the formation of the bubbles. When the P2 pressure recovers above the vapor pressure, the bubble implodes or collapses. I can quickly show you a quick video of how this looks like. And you will see there the bubble gets some pressure from the top, indented, a jet forms, and it pushes the bubble and it implodes. So going back to the slide. So what we see is the implosion of the vapor bubble. Liquid microjets form. Liquid microjet from the recovering pressure creates an indentation in the bubble. These microjets burst through the bubble, and the implosion and the collapse also cause pressure waves up to 1000 psi. The combination of the microjets and the pressure waves cause mechanical damage to the plug in the seat and the body, as well as the valve body, yes. It also causes noise and vibration, loss of efficiency, and loss of process control. So in this picture, you can see where it implodes. At this bottom picture, you can see where it implodes against the wall of the valve. And this is where it will physically damage your valve at high speeds. Yes, so stages of cavitation, there is different companies do different things. There's for us 3 stages. First is the partial cavitation, non-choked condition, and the excessive part cavitation, also non-choked conditions. Both of these conditions would be easily solved with a hardened plug and seat configuration, and it is straightforward. Also, you can do staging in this case if you need. In the next pressure, when the pressure differential across the valve is much larger, you get choked conditions and full cavitation. This is more severe and need to be addressed in a different format. We can help and assist you with a solution for this at the time of this condition. What I want to show you on this graph is that the higher the delta P, the more severe the cavitation effect is on the valve. Okay. Cavitation not always cause damage. Damage will occur when, as I just said, the intensity of the cavitation is high when the delta P is high. When materials used in the area of cavitation are not hardened, hardened materials reduce the damage. Continuous exposure to cavitation. So if the valve is continuously exposed to cavitation, then the long-term effect of that would be horrendous for the valve. The valve size, larger valves sometimes make it worse because the valve will control to a more close position to the seat, and wear will just cause the trim to be damaged more. The wrong design of the valve and trim, and leakage occur between the plug and seat. When leakage occurs between the plug and seat, you obviously have a high pressure going down to a low pressure. This will cause cavitation, and that will damage your valve. So preferably you will need to look at leakage. Cavitation is caused by fluid pressure, not by flow. This is very important to note. On the picture on the left, you will see that at the valve at 25% open, the cavitation occurs close to the seat area. As the valve opens more, the cavitation actually moves downstream of the pipe. And that is interesting to see that the flow just change the location and not the effect of the cavitation. Good. So I'm going to go to Stefan now. How Raman overcomes cavitation. He's going to address the first point for us.
Yeah, so as you say, there is several stages of cavitation. So you have first incipient cavitation, and then you have severe cavitation or choke cavitation, as we say. So we will see in the program, actually in our sizing program, that it will state which stage it is. And most often, when you have incipient cavitation, this can be definitely be solved, or actually we can handle it by using our model KS1B, which is our metal seat design. So it's a sterile seat, full sterile seat with hardened ball sector. So the ball sector is treated with expandite treatment, which increase the hardness. So typically it increased by 5 times more the standard hardness of stainless steel. So typically, incipient cavitation, we can use our model KS1B, and that will definitely solve the problem, meaning that the cavitation itself will not have any effect on the valve. So you won't have any damage on the ball sector or the seat because of the parts which are hard enough. 1C is a little bit more complex or more robust because we have some other parts in the valve which is treated, which is our seat holding ring, which is basically the cover on the body, which is also in contact with the media, of course, and we treat it also with expandite treatment to also increase the hardness. So that's actually very robust design that can definitely overcome the incipient cavitation. All right, Ryan. Yep.
Good. So the second way to do it is to stage the pressure drop. By staging the pressure drop, you actually reduce the vena contractor going through the vapor pressure. So we're going from P1 to P2. The pressure doesn't drop that severely, and it doesn't go down to the vapor pressure. And then on the second stage, you go from P2 basically to P3, and your overall P1 to P2 is then without no cavitation. So a restriction orifice is a good solution in this application, especially where there's constant flow conditions or not high varying flow conditions. So yeah, good solution to solve the problem. Stefan, will you take this one for us?
Yeah, so that's typically when you have severe cavitation, when you cannot stage the pressure drop. You may have, for example, stories, you have particles in the media and so on, so you may not be able to use an orifice. And then what we can provide in that case is our model KS1E. So it's actually also a stellated seat ball sector valve, which is always fitted in reverse flow. So that's basically the picture on the bottom left. You see actually on the top left what it should be, normal direction. So the flow enter on the right and exits the left, and you have possibly the vena contracta inside the valve. But if you put it in reverse flow, the bottom picture, then you have actually the vena contracta outside the valve, which means that the cavitation will happen outside the valve. And as a result, of course, the body, the ball sector and so on will remain intact because no cavitation will actually happen inside the valve. So that's something sometimes that we provide whenever we have customer looking for solution with similar products having damage on the body or the board or the plug, whatever. Then we provide our most robust solution, which is our model KS1E. We put it in reverse flow at the bottom left, and cavitation will happen outside the valve, definitely protecting the body, and you will not have any damage inside the body. So that's a way that we can solve it as well.
Okay. Yes, and then there's a rule that location. It doesn't just allow us to in property, but also in valves. It's important that you always look at when you have cavitation, how many downstream straight pipe you have. There's a recommendation of 4 to 8 in normal cavitation. In full cavitation or severe cavitation applications, anything from 8 to 16 pipe diameters. Also look that there's no elbows. Make sure that that is out of the way. It just helps your valve and your whole system a lot when it gets to cavitation. All right, now let's go back to the sizing, which we've done. So now we see that we have cavitation here, and we're going to select our valve and select the valve that we're going to select, and we're going to start with is the KS1, and we selected the DN100 because we know that this is going to work.
Yeah, so
the program is designed.
Yes,
the program is designed in such a way that. Sorry, Stefan.
Yeah, just saying that the KS1 is a soft-seated design.
Soft-seated valve.
We do not
yes.
know.
Yeah. So let's try this. So immediately we see soft-seated is exclamation mark. It says that valves with soft-seated are not suitable for cavitation applications. We also, if I go to the overview, we see that our reliability index is 1. Stefan, will you discuss this for us quick?
Yeah, this is actually to show you whenever you use this sizing, you may find this RI index being read like that, high value, and you don't know what it is. So you see on the right you have this help window that's very convenient. You just need to click on somewhere and you will have actually any information about what it is. So in that case, Lauren, click on the RI on the left panel, and we have information about the reliability index actually. So right now it's 1, and basically the reliability index is calculated by the software itself. So it takes all processed data, so of course pressure, temperature, and so on, flow. Then you calculate the velocity of the valve, inside the valve, the noise level, possibility cavitation, and so on, and end up with an index. And basically, you always want to have this index as close as possible to 0, because if it's increased too high, for example, closer to 1, for example, then you may have damage. You may have possible damage inside the valve. It's an index, of course, so it doesn't mean that you will have damage, but you may have damage. But anyway, you always want to have it closer to 0, and basically here it states that between 0 and 0.1 it's not a problem, and higher to 0.1, then you have to check carefully. Here is 1, so it's quite high, and clicking on the exclamation mark here, yes, actually you can see it just pop up a small window that this is due to the cavitation. So 99% of the reliability index is due to the cavitation. So it's not noise, it's not velocity, whatever, it's purely cavitation. And as we stated, this is incipient cavitation, as we see actually in the overview, I think. Then if you go to the overview on the right, because then you can see actually the stage of cavitation. You will see incipient cavitation. And as we told you, just using a model 1B metal seat design will probably solve this issue. So if you look at model 1B, then we'll see what will be the new reliability index. Just use no filter. Yeah. So of course, there is a lot of models, and if you don't know which one to select, you're always welcome to come back to us and ask us. All right, now it goes to 0, meaning that it's not a problem at all for the valve. It can handle it.
Okay. All right. Now, so from here, I just want to go through this again. So from here, you can look at the flow curve. We'll see where the valve is open. The valve is open between 40 and almost 60%, which is good for this application. No cavitation, reliability index is 0. And now you can just send this and just print, and you just send this to us now. Sorry, I can't.
Yeah, you have the send calculation by email on the top. Huh?
Yeah. On email.
Right.
This one, yeah, there. Okay, it moved.
That's the one. If you want to get the PDF and so on, just click on it, and Yes, here you have a
Let's see.
pop-up appearing,
Okay.
and then you can send it. Yeah, and then you receive a copy with PDF and so on, so you can use it as well.
Okay. Good.
All right.
Any further questions?
Good. I think yeah, that was what we wanted to show you.
Is there any questions?
You're
Can
welcome
we
to ask
see?
any question. Yeah. And also, if you are looking for other topics or similar topics regarding sizing, please let us know. We are very you are welcome to suggest any other topic which we can consider, of course, to make new webinars.
Yes.
Also, this webinar is recorded, so it will be also available on YouTube. So I think after the meeting, after the webinar, you will receive an email with a link and so on.
Good.
Right. Someone is raising their hand, but you need to ask a question on the chat function actually. So you have the chat on the top. Just click on it and just you can write your question. All right. No questions then, or yes. So orifice plate. In the sizing tool we have, there is no possibility to size orifice, but we have actually the full version, of course, of Conval, which allow actually to size the orifice. So I don't know, Ryan, if you want to talk more about orifice plates in Conval.
At this stage, yeah, I can't. We have to open Conval for that, but we can
just yeah.
Oh, to size. Yeah, for us it would be just when we take the valve, we calculate the differential pressure. We will then calculate the differential pressure that's required so that we're out of the cavitation zone. We look at the differential pressure across the orifice and then we'll size it accordingly, and then we'll give you some details regarding that.
Absolutely. So whenever, if you have any requirement for that, of course, we just need the basic process data, so inlet, outlet pressure, flow and temperature, and then if we find out that we have severe cavitation, we need to find any solution, then we can do the sizing with orifice. And then we can suggest the valve and the orifice size.
Yes.
Then what is the material recommended as a trim for avoiding cavitation? So as we say, you need to have some kind of hardening on the trim. So in our case, our ball sector valve, as standard, we use stainless steel or 254 SMO. That's the base material, but it's not hard enough. So in that case, we use Expanite, which increase the hardness. And as I say, typically 5 times more hardness than standard stainless steel.
Yes. And I just want to comment there, the trim will not avoid cavitation, it will just resist the damage.
Absolutely. It will not avoid cavitation, it just take care of the impact and so on. And the harness will be such that the impact will not affect the material. Other question I will answer separately, of course.
Yeah. Okay. Any other questions? Good. All
right. But if you don't have any other question, then we'll end this meeting. You will get the link with the video and so on. And again, please contact us if you have any interest about other topic about sizing. We can think about other topic. That's not a problem. We can always support you with other webinars.
Yeah.
All right.
Thank you.
Right. Thank you. Everybody.
Bye.
Bye.